So, um, in 3.8, we're going to talk about implicit differentiation. Up to this point, we have been doing derivatives, and you might have noticed that all of our equations said y equals or f of x equals. They had been explicitly solved for y. So it was y was a function of x, and we were allowed to do that derivative and only focus on what happens to the x's. Well, 3.8 starts to look at functions where the x's and y's are kind of mixed up, and that it would be very difficult, if not almost impossible, to solve for y. So the x's and y's might be multiplied, the x's and y's might be all mixed up, and so we need to know how to deal with functions where it's not so clear cut that it's y equals. Examples of a perfect function like that: a circle equation, x squared plus y squared equals 4. That's an equation of a circle. It's not explicitly solved for y, and when you go to solve for y, you get plus or minus a square root. So what do you use, positive or negative? So implicit differentiation kind of fixes some of those issues. So there are 5 main steps that you want to take when solving a implicit differentiation problem. If you cannot explicitly solve for the y, so if the x's and y's are mixed up, take the derivative of all the terms. Keep in mind that y is a function of x and requires a y prime every time you do it. So if you have y squared, the derivative of that is 2y times y prime. So every time we take a derivative of a y, we're going to tack on a little y prime. And remember that if x and y are touching, that considers itself a chain rule. That's a product. That's x times y. So get all the y prime terms to the left and all the other terms to the right. We're going to factor out a y prime, and then we'll be able to solve for that y prime by dividing both sides by what is with the y prime. Now that sounds like a lot of stuff, so write down those rules, and then we'll actually talk about where to go from there and how to follow those steps. Every time you take a derivative of a y, tack on a y prime. That's the main takeaway from all of this. And then you just use algebra to solve for y prime. So now let's actually just take a minute and let's try a few and you'll start to see it. Okay, so what we're going to do is you're going to take derivatives using all the rules we've done so far. You may have product rules and quotient rules to do. If you take a derivative of a y, you always tack on a y prime. That's the main thing to take away from this. Because y is some function of x that we can't quite determine, you make it y prime. Okay, so every time we take a derivative of a y, we're going to tack on a y prime. That's the main idea from this. Okay, so let's talk about this. It's kind of funny. It's like I knew what they were doing. They have an equation of a circle. X squared plus y squared equals 25 is a circle with its center at 0, 0, and a radius of 5. And they want us to find dy dx. What is dy dx? That is the derivative of y in terms of x. You can also call that y prime if you like. Okay, that notation will come into play when we do some applications of implicit differentiation called related rates. We need that dy dx terminology. If we do something called differentials, we'll need that terminology. But for now, we can just call it y prime. So if we have this function, you'll notice it does not say f of x equals or y equals. We can't technically really solve it in a good way for y. So this is what we're going to do. We're going to take the derivatives of x's and constants like normal, but if we take a derivative of a y, we tack on a y prime. So this is going to be 2x plus 2y times y prime equals 0. So it's not a hard process. Here's where we can make some mistakes due to our algebra. We are going to solve for y prime. So that's what I meant with if it didn't have a y prime on it, we're going to move it to the other side. And then whatever factors are with the y prime, you divide off. So now it's just algebra. So that is what y prime is equal to. What's interesting, you might find, is that our derivative has x's and y's in it. It's not just, it's determined by both of our points. Now that still represents the slope of the tangent, but you'll have to plug in the x and the y to find it. So if we continue with this same problem, but in B it says find the equation of the tangent line at the point 3, 4. The first thing we're going to do is find the slope of the tangent, but we have to plug in an x and a y. So it's going to be negative x over y. So our slope of our tangent would be negative 3/4. We still do the same thing we always do with slopes of tangents and tangent lines. The first thing we do is find our derivative. Second thing we do is find the slope of the tangent. Third thing we do is y minus y1 equals m times x minus x1. And we've already done those things. We found y prime. We found the slope of our tangent. So we're on really technically step 3. So our point is 3/4. So it's y minus 4 equals negative 3/4 times x minus 3. Now, I don't need you to do anything else with that. I know you know that's an equation of a line. I know you know to get it prettier, you could distribute the negative 3/4 and add 4, but don't feel that you have to go any further. Is that the equation of the tangent line? Sure is. I know by now that you can do algebra. At least that's my hope. So I'm not worried about you rearranging anything. Okay. Everybody okay with our first example? Any questions? Okay. Let's look at another one. Now, again, it says, assuming that y is defined implicitly by the equation x cubed sine of y plus y equals 4x plus 3, find dy dx. Again, that's just y prime. Now, eventually, that notation, we're going to have to use that exact notation, but there's no need right now. I'm going to rewrite this a little larger, but I'm also going to include a dot between those two things. Now, the reason I always like to put that dot there is this requires a product rule. So I got to do that product rule on that piece, or it's just not going to work. When I do a product rule, if it happens to be a y, I always have to include a y prime in its derivative. Okay. So if I do the product rule on that piece, it's the first times the derivative of the second. So it's just a cosine of y times y prime. because I don't know what y is. I don't know what y is, so I have to include a y prime. Plus the second times the derivative of the first. And now I'm ready to finally move on to the rest of my equation. The derivative of y is y prime. The derivative of 4x is 4. The derivative of 3 is 0. Okay. Now, if you went back and looked at the rules you wrote, or the steps you wrote down, I mentioned that any term that contained a y prime, we're going to keep on one side, and we're going to move all the other terms that do not have a y prime to the other side. So these two terms do not have a y prime on them, so we're going to move those to the right, and then we're going to keep these terms, and if there were any on the other side, we're going to keep those on the left. Okay. So if I do that, I'm going to rewrite these a little nicer, but it's going to be x cubed cosine of y, y prime, plus y prime equals 4 minus 3x squared sine of y. So I just moved that to the left, rewrote those a little nicer. Okay. Now, the reason we do that is because we have to solve it for y prime. We want our final answer to say y prime equals whatever. So y prime equals means let's factor out that y prime so that it's completely alone. So we get x cubed cosine of y plus 1. Now don't forget the plus 1, because the plus 1 would be what would be needed there if we redistributed to get this here. So if you factor out a y prime from y prime, always leave a 1 in its place. Now y prime is being multiplied by that quantity, so how are we going to get rid of this quantity? We just divide it off. And that's what the last step said. And so y prime is just 4 minus 3x squared sine of y over x cubed cosine of y plus 1. So you'll notice we have x's and y's all mixed up. But that's always the steps you're going to take. So let me go over the rules one more time. If anything is touching related to both x's and y's, you have to use the product rule. We're going to take the derivatives, including a y prime every time there's a y. Then we're going to keep the y prime terms on one side, the non-y prime terms on the other. You're going to factor out a y prime, and then whatever is left in the parentheses divides off. And that pattern happens again and again. We're going to see that pattern happening over and over. Any questions about that process? It's weird. It's definitely a process. Let's do it again. Now, this equation is called the folium of Descartes. You know the Cartesian plane? You've heard of Cartesian plane? Descartes was a French mathematician a long time ago. This folium of Descartes looks like that. Isn't that pretty? And we are looking at the tangent line right there. Okay, so that's just a depiction of what that equation is. Okay, just so you had a little picture. Anyway. Oh, you don't have the picture. Well, you can see the picture. I'll show you in a minute. I'll show you a little more in a minute. Okay, so it says find the equation line of the equation of the line tangent to the graph at 3/2, 3/2. So what do? Well, first thing you should notice is our x's and y's are all mixed up. So remember, first step is to find y prime. So we're going to make what piece look more like a multiplication so we don't forget the product rule? Exactly. So rewrite 3xy as 3x times y. And I always just include the 3 on the x, but you can include it either on the x or on the y and it will work. So every time we take a derivative of something with a y, we are going to include a y prime. So this is 3y squared y prime plus 3x squared. Now we're going to use the product rule on that piece. So when we do the product rule, remember, just include the negative 3x as one piece and the y as another piece. So it's the first times the derivative of the second. Well, I don't know what a derivative of a y is, so I just call it y prime. Plus the second times the derivative of the first, and then the derivative of 0 is 0. Okay. Now, we are going to take all the terms that contain a y prime. We're going to put those on one side, and anything that doesn't contain a y prime, we're going to move to the other side. Okay? Yeah. Anytime you take a derivative of something that originally was a y, tack on a y prime. So when I did this derivative, I got a y prime. This derivative here, when I did first times the derivative of that piece, I tacked on a y prime. So anytime you take a derivative of a y, it gets an extra little piece. It gets a y prime. It just automatically, oh, I'm doing a derivative of a y, whatever it normally should be, times y prime. Just tack on a y prime, okay? So the ones that I've highlighted kind of in that yellowish greenish color, we're going to keep on one side. Anything that does not contain a y prime, I've kind of highlighted in that purple color. I'm going to move to the other side by subtraction and change its sign. So the last piece is a negative 3y. It's going to become a positive 3y. The 3x squared is going to become a negative 3x squared. And then what have we done before? Well, you need to factor out the y prime exactly. So we're going to factor out the y prime. And then how do we get y prime by itself? Well, that factor there needs to be divided off. So you will see that pattern is going to happen every time. And don't worry about reducing. What are both everything on top and everything on the bottom divisible by? Yeah, so you could technically divide everything by 3 if you want. It'll take care of it when we go to use the derivative. So feel free to, it doesn't matter. Okay. So the second step is to find the slope of the tangent. Now remember, we are using the point 3/2. So wherever the x is, we're going to put a 3/2. Wherever the y is, we're going to put a 3/2. So let's go ahead and put 3/2 in. The y value is 3/2, so 3 times 3/2 is 9/2. And then we have 3 times 3/2 squared. 3/2 squared is 9/4 times negative 3 is negative 27/4. And then this is going to kind of be the flip-flop of that. So this is going to be 27/4 minus 9/2. They are exact opposites, and if you simplify it down, you get the slope is -1. And you can throw it into a calculator if you have the urge to check, but it's going to be -1. And then remember the third step, we just use y minus y1 equals m times x minus x. So our slope is -1. Our point is 3/2, 3/2. So our final answer for the equation of the tangent line is y minus 3/2 equals -1 times x minus 3/2. And you could put both the original equation, this equation here, into Desmos exactly as it was originally given to us. You could put this equation, just like you see it here, into Desmos, and you should see that it is the tangent line at 3/2. Okay, so this just allows us to find derivatives, slopes of tangents of very complicated equations that before this time we really could not do anything about. Okay, so if you do a derivative of a y, tack on a y prime, but otherwise it follows all the same rules of derivatives of x's. Any questions there? Anybody have any questions that you? Nope. If you want to, but no. It just, you can check your work in Desmos. If you put the original equation, the tangent line should hit it at the point that you have been given, and it should appear as a tangent. It should, hit it nicely. Okay. Now, a lot of these will be word problems. We're inching toward the word problems. I am more concerned initially about not necessarily the word problems, but can you do the implicit differentiation? That's something I'm really concerned about. Okay, so we have this video game where a rocket is traveling in an elliptical orbit, and it says that the object of the game is to destroy an incoming asteroid traveling along the positive axis towards 0, 0. If the rocket fires a missile when it is located at 3, 8, 5, will it intersect the x-axis? Okay, so first thing we want to find is that what's y prime, okay? So what we want to do is, so we have our equation, and we're trying to see if it's going to intersect the x-axis at that point. So let's take the first derivative in terms of x. So remember to tack on a y prime. So we get 8x plus 50y, y prime equals 0. Now, if we solve that for y prime, that one's a little nicer even than the last one. We can subtract off the 8x and divide by 50y. Now, both 8 and 50 are divisible by 2, so I would divide by 2. You don't have to, when you simplify the slope of the tangent, you will find that. Now, let's think about what the slope of the tangent is at that point. So if this is our point, what is the slope of our tangent? Okay. The slope of the tangent is, if we use this, it would be -4 times an x value of 3 over 25 times an x value of 8/5. And if we reduce that down, you get -3/10. So what is the equation of the tangent line? Well, the equation of the tangent line, I have solved it for you. If we did y minus y1 equals m times x minus x1 and made it a little prettier, that's what we would get. Okay. Now, let's think about where it is going to hit the x-axis. So where will it hit the x-axis? Well, it hits the x-axis. Think about the x-axis is where our y value is equal to 0. So this tangent line, it's going along that line. Let's look at where y equals 0. Well, we have to, it's not where x equals 0, it's where y equals 0. So we're going to get 0 equals -3/10 x plus 5/2. Now, when I look at that, if I don't want to have to use a calculator, I like to multiply through by the common denominator of 10, which gives me -3x plus 25. And then I can just solve pretty quickly from there. So we get -25 equals -3x, and x equals 25 over 3. So if we fire the rocket at the point 3, 8/5, we follow that tangent line, and that tangent line hits the x-axis at 25/3. or I'm sorry, the y, yeah, the x-axis at 25 thirds. Okay, so that is implicit differentiation. It's kind of weird. There can be a lot to it, but you know, it is what it is. Okay. Okay, now you have just one kind of word problem or two word problems. The rest are implicit. You just need to practice that. Okay, so there is 3-8. Do your thing and good luck.